In the previous lecture, we spoke about a concept known as thermal expansion, and we spoke about one type of expansion known as linear expansion. Now we're going to examine a second type of expansion known as volume expansion. Now, when a substance, and that includes solids, liquids, and gases, undergoes a change in temperature, it either expands or contracts depending on whether or not the temperature increases or decreases. So, let's suppose we begin with the following solid object that has an initial volume given by V0. Let's take a candle, a heat source, and let's heat our object. So we increase the temperature. So after some time, the object will expand outward in all possible directions, and this is known as thermal volume expansion. So the reason the object expands is because the individual atoms and molecules inside our solid object will vibrate more vigorously, and that means the distance between any two adjacent atoms or molecules will increase, and that collectively will increase the entire volume of our object. So if the initial volume of the object is given by V0 and the object expands by a volume given by delta V, then the final volume of our object is given by V0 plus delta V. Now, in the same exact way that we were able to develop a formula for thermal linear expansion of objects, we also have a formula for thermal volume expansion of objects given by the following equation. So the change in volume that our object experiences is equal to the product of the change in temperature, the initial volume V0, and beta, which is the coefficient of volume expansion. And this value depends on the type of substance that we are using. Now, this equation only holds as long as the delta V is much smaller than V0. So, let's suppose that we are talking about isotropic solids. Isotropic solids are those solids that have the same exact properties in all different directions, such as density. Now, if our solid object is in fact isotropic, that means we can approximate the beta value to be approximately equal to 3 times the alpha, and alpha is simply the coefficient of linear expansion that we spoke about in the previous lecture. From this approximation, we have the following formula. The change in volume is approximately equal to, we replace our beta with 3 alpha. So 3 alpha multiplied by V0 multiplied by change in temperature. So why is this true? Well, we're going to prove this in the following several steps. But first, let's make the following assumption. Suppose that we are dealing with an isotropic solid, and suppose that we are dealing with a solid that is a rectangle that has a height given by h0, a length given by l0, and a width given by w0. Using these parameters, we can calculate the initial volume V0 of our solid rectangular object by simply taking the product of these 3 lengths. So length, the height, and the width gives us the initial volume. Now let's suppose we take a heat source, for example our candle, we heat the object, and after heating, each side of our rectangular object will increase by a factor of our alpha multiplied by delta T. This is what we spoke about in the previous lecture. So that means every single one of these sides will increase by that factor. So we have the final volume given by V is equal to H0 multiplied by L0 multiplied by W0, and every single side is increased by this amount, 1 plus alpha multiplied by delta t. So let's call this equation 2. Let's call this equation 1. Then if we want to find the change in volume, we simply take the final volume after heating and subtract the initial volume. So equation 2 or equation 1 minus equation 2. We have V minus V naught. So we're subtracting V initial from V final. And this is equal to, well, we have this entire equation. So let's combine a few terms. Let's combine these three identical terms and we get H naught, L naught, W naught multiplied by 1 plus alpha multiplied by delta T, and we raise it to the power of 3 because we have three identical terms. And then we subtract equation 1, so we subtract V naught. Now, notice, according to equation 1, H naught times L naught times W naught is simply V naught. So we replace this with V naught. And we have delta V, our change in volume after heating, is equal to V naught multiplied by 1 plus alpha times delta T to the third power minus V naught. So notice V naught appears on both terms, so we can take that out and we get the following result. Delta V is equal to V naught multiplied by 1 plus alpha times delta T to the third power minus 1. Now, if we expand the following equation and multiply it out, we get the following result. So we expand it as shown, we multiplied, we add things out. Notice the ones will cancel, and we're left with the following result. Delta V is equal to V naught multiplied by 3 times alpha times delta T plus 3 times the square of alpha times delta T plus the cube of delta times change in T. Now, if the amount of expansion is much smaller than the size of the original object, if the delta T is smaller than V naught, then this term becomes very, very small, because our change in T multiplied by a very small value of delta gives us a number that is much smaller than 1. And that means a number that is much smaller than 1 to the square is a small number. And that same number to the cube is also a very small number. So these numbers are very small, and we can approximate this value to be very close to 0. So that means we can cross these out and we get the delta V, the change in volume of our object, is approximately equal to V naught multiplied by this term. 3 multiplied by delta multiplied by change in T multiplied by V naught. So once again, we can make this approximation because these two values are assumed to be very small.